Okay, well, I think probably ought to get started. Now, remember then, Wednesday we have our little written exercise. And currently what I have are about 40 multiple choice and 5 short answer things. And it's all dealing with chemistry, but it does include organic compounds we want to talk about today. So without further ado, we'll get started with that. Now, there are several classes of organic compounds, and the thing we want to know as we go through these now are what are the characteristics that distinguish and identify them. We're going to be seeing these again and again, particularly when we get on to the next topic, which will be metabolism and the cells. And so, without further ado, away we go. Well, first of all, when it comes to organic compounds, they are primarily based on carbon. Carbon is common in every one of these. There are a few other elements that are going to be added in, and all of them are going to turn out to be, of course, covalent compounds. So they're made of covalent molecules, all right? So, what are some of the other elements that we have? Well, in addition to carbon, which is always there are such things as oxygen, hydrogen, nitrogen, phosphorus, and sometimes sulfur. And that's pretty much it. Now, as you recall, all of these things are non-metals, all of them. So, they are going to be non-metal compounds, and as we well know, non-metal compounds are essentially going to be covalent compounds that use covalent bonds. Alright, so carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Those are essentially the elements that you're going to see in these types of compounds. Now, when it comes to them, as we said, we have things like carbohydrates, lipids, proteins or amino acids, which proteins are made of, and nucleic acids. And then there's one more that we can add that isn't on this list, but we're going to get to it, and that's what we can call energy compounds. Alright, so we have carbohydrates, lipids, proteins and amino acids, nucleic acids, and energy compounds. And those are the major classes, really, of these organic compounds that we're going to deal with. Okay? Alright, so continuing on, let's get to the first class now, the carbohydrates. Now, if you get out your terminological dissecting kit and you take a look at that word, you see carbon. Alright, now remember, if they're organic compounds, carbon is the primary basis on which they're built. And hydrate. Well, hydrate refers to water. So it's kind of like carbon and water. Well, what are the elements that you find in water? Hydrogen and oxygen, and in that 2-to-1 ratio. And there you go, because that's one of the big hallmarks of carbohydrates. They basically contain these 3 elements: carbon, hydrogen, and oxygen. And the hydrogen and oxygen are going to be in a 2-to-1 ratio as you find in water. Now, it doesn't matter how many hydrogens and oxygens are there. There's going to be more typically than 2 and 1. But they're in a 2-to-1 ratio. Alright? So, 3 elements, carbon, hydrogen, and oxygen in a 2-to-1 ratio. If it has those characteristics, it's a carbohydrate of some ilk. Alright? Of some description. Now, we can call these different things. They're what we can call simple sugars. Alright? And then we can have the starches. So there are the simple sugars and the starches. Simple sugars are monosaccharides, basically, and polysaccharides are the starches, which are really nothing more than a polymer, which is just repeating units of the same thing. In other words, in this case, typically glucose, repeated one after the other in a chain. So you just chain together a couple of hundred or 1,000 or so of them, and you've got a polysaccharide. Poly, of course, literally means many. Saccharide means sugar. Alright, so there we go. Alright, so let's take a look at some examples of these. And when it comes to the simple sugars, we start off with what are called monosaccharides. Now, again, Get out your terminological dissecting kit. Mono means what? One. Saccharide literally means sugar. All right, you cannot break these down into anything smaller and still have a simple sugar. All right, they're as low as they go. It's a monosaccharide. That's as simple as it gets. Yeah, you can break it down, but you'll not have sugar if you do. All right. So now, when it comes to these, the principal ones include such things as glucose, and we're going to see this one over and over and over again. Fructose is another one. Galactose is another, and then we have two more. We have ribose and we have deoxyribose. And here's just another little trick. You know, if it has deoxy, I wonder what that means. Remove an oxygen, right? Well, you take a ribose and take an oxygen out of it, you've got deoxyribose. I mean, pretty simple. Those are the principal monosaccharides that we're going to deal with. All right? So, we have glucose, fructose, galactose, ribose, deoxyribose. All right, now, there are a couple of ways then to classify them, or as I like to say, slice and dice. So, let's take a look at that. All right, one way that you can classify these monosaccharides are according to the number of carbon atoms which they contain. All right? And so, we can have what we call pentoses. A pentose. Pent means 5. So, a pentose is a 5-carbon sugar, a 5-carbon monosaccharide. And out of that list that we just had, we have ribose and we have deoxyribose. All right? Ribose and deoxyribose. Those are both pentoses. All right? And those are the principal pentoses that we're going to see a little later on. We're going to put to use, particularly when we get to nucleic acids. Hexoses. Hex meaning 6. Well, 6 carbon monosaccharides. What do we got here? We have glucose, fructose, and galactose. Those are all hexoses. All right? So, the 2 pentoses of preeminence that we're going to deal with, ribose and deoxyribose, and then the hexoses that we need, the 3 that we need to remember, glucose, fructose, galactose. All right? And we're going to put them to use here very, very shortly. All right, so there we go. We can classify them according to the number of carbons. And the ones we're going to be most concerned with of the monosaccharides are the pentoses with 5 carbons and the hexoses with 6. Now, let me just digress a moment. I see a bunch of people feverishly writing. Now, if you have the outline that I put on the web page, a lot of this stuff is already there and you don't have to recopy it. You can just add to it so you won't have to write quite so feverishly. Okay? Now, here is a structural formula, and don't go into heart failure. I'm not going to expect you to draw this out from memory for me, not in this class. There we have glucose. How many carbons did we say it has? 6. 1, 2, 3, 4, 5, 6. There they are. All right? Now, you notice the only other things that are here are oxygen and hydrogen in addition to the carbons. And if you count, you're going to find the hydrogens and oxygen in a 2-to-1 ratio. Now, the molecular formula for this would be C6H12O6. All right? So if you count them up and wrote it as a molecular formula, it would be C6H12O6. Now, take a look at that. How many hydrogens are there? 12. How many oxygens? 6. All right, that's in a 2-to-1 ratio, is it not? Carbon, hydrogen, oxygen are the elements. The hydrogen and oxygen are in a 2-to-1 ratio. Carbohydrate. There we go. Why is it considered a hexose? Why is this a hexose? 6 carbons, right. Now, another way to show it, and again, don't go into heart failure. This is the ring form. Now, this is typically how it actually exists. rather than that linear chain. And again, if you count, there are the 6 carbons. One of them is not in the ring, it's above it, so there are 5 in the ring along with an oxygen over here. And so there we are, and then we can condense it down one more step into this simple little ring-like structure. All right, it's a 6-member ring, 5 of them are carbon, so it's just understood there's a carbon here, 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 and there. And there is the oxygen. So this is just a condensed way of showing it. All right, and you don't really need to worry about that. All right, now let's kick it up a notch and let's go with what we can call a disaccharide. Now, again, get out your terminological dissecting kit. What would the prefix di mean? 2. All right, what is it? It's essentially 2 monosaccharides linked together. That's how you make it. All right, so these are composed of 2 monosaccharides held together by what we call a glycosidic bond. Now, in order to put those 2 monosaccharides together, we undergo what is called a dehydration synthesis. Dehydration synthesis is involved in taking 2 monosaccharides and sticking them together to form a disaccharide. What does the term dehydration mean? Remove water. That's exactly what you do. You take the 2 monosaccharides, you take out a molecule of water between the 2, which means you're going to take an OH off one of them and an H off the other. That removes a molecule of water, and that puts them together. Now, what if you wanted to break them apart back to monosaccharide units? What would you do in a case like that? Add the water back. Exactly. And the term for adding back water and breaking something apart? Hydrolysis. So we use dehydration synthesis to form a disaccharide from 2 monosaccharide units, and you would use then hydrolysis to break them apart back into 2 monosaccharide units. The body does this all the time because you cannot absorb disaccharides. You can only absorb monosaccharides from the diet. All right, so we do it with an enzyme in the case of the body, but nonetheless, it is a hydrolysis kind of reaction that takes place there. Now, what are the principal ones? Well, there are really 3 of these. Maltose is one. What's maltose? It's 2 units of glucose held together by a saccharolytic bond. All right? So you take 2 glucoses, you put them together, take out a molecule of water, you've got a molecule of maltose. Now, it's pretty simple, isn't it? Now, maltose, well, it's from malt, all right, so it's a grain sugar. All right, another one we have, lactose. Well, what's it? It's a glucose and a galactose. I don't know why I've used one here and wrote it out there, I don't know. But anyway, there you go. 1 glucose, 1 galactose. Put them together, take out a molecule of water. What have you got? A lactose. Now, where do you find lactose? Milk. It's the primary sugar in milk. All right? So, we have an enzyme that will hydrolyze that. You take in milk, the enzyme hydrolyzes it back to glucose and lactose, and then you absorb those 2. Now, as you well know, a lot of folks tend to lose that enzyme as they age, and they become lactose intolerant because they can't do this. They can't break them apart, and then you end up with gas, indigestion, and all that stuff, all right? And here's a biggie, sucrose, table sugar, all right? 1 glucose, 1 fructose, all right? So if you have a sucrose molecule, it's formed by putting together a glucose and a fructose, take out a molecule of water. When you ingest sucrose, which you do, you sprinkle it probably on your cereal in the morning, there's an enzyme that's going to hydrolyze it back to a molecule of glucose and a molecule of fructose. Now, we need to keep in mind what monosaccharides are used to form these, and which monosaccharides you're going to get for your efforts if you hydrolyze them. All right? Simple, isn't it? Because you're going to see these over and over and over again. And as my mother used to say, you'll never learn it any younger, so you might as well learn it now. All right, now here is just a condensed way to draw a disaccharide. Again, I don't expect you to have to do this, but here we go. There are the two monosaccharide units. There's the glycosidic bond. In other words, what's happened is a hydrogen came off one of these and a hydroxyl off another, and what's left, well, there it is. There's a glycosidic bond holding them together. All right? Now, polysaccharides, and as we said, poly means many. These are typically formed by linking together glucose units in a chain. And there are really two ways to do it, two kinds of chains that can result. All right, and these things can be, thousands of glucose units in length. All right, so what have we got? Well, one kind that we can have are what are called amyloses. And amylose is a linear chain of glucose units, one right after the other. All right, and these are linked together by those glycosidic bonds. So every time you add another glucose onto the chain, what do you have to eliminate in order to stick it on? Water, a molecule of water, that's right. All right, plants typically make these. Now, amylopectins, these are branched chain starches, branched chain polysaccharides. Plants can do it, animals certainly do it, and here's one that you probably have made earlier this morning, something called glycogen. Sometimes animal starch is the term for it. Where is it made? It's primarily made in either liver or muscle cells, and that's where it's stored. And guess what it's for? Well, it's a way to store excess glucose. And so when you get between meals, what do you suppose is going to happen to the glycogen that you made and stored in your liver and muscles? You're going to break it down into glucose units and use it. That's right. So, in other words, this glycogen is what's going to help maintain blood glucose levels between meals. You have a meal, you take in a lot of glucose, more than you can use right then, so you make this glycogen and store it, and then when blood glucose levels drop, you start breaking down the glycogen and reforming glucose. Now, how would you get from glycogen to glucose, I wonder? Add water. So again, hydrolysis. All right? There you go. All right, now, cellulose is another example of a polysaccharide. Now, only plants make that. What is it? Well, again, it's a polymer of glucose, but it's held together by a slightly different glycosidic bond. One that we cannot break apart. All right? So, cellulose, well, that's what plant cell walls are made of. And so, if you're munching away on a stalk of celery, you're getting a lot of this stuff. But you can't digest it. So, it just passes right through as an insoluble fiber, which is useful, in our dietary sense. But we don't get any nutrition from cellulose because we cannot hydrolyze it. We can't break it down. Now, who does? Well, ruminant animals like cows and sheep certainly do, but they don't do it directly. They have organisms in their first stomach compartment called the rumen that actually does the work. That's why they lay around chewing the cud, as a way of helping to digest it, because it takes some time to do it. It's not a fast process by any stretch of the imagination. Termites too, but they don't do it directly either. They have a little protozoa in their gut that does the digesting really of the cellulose. But in any event, there it is. So it's also a polysaccharide, but it's one we can't break down. Starches, glycogen, yeah, we can break that down. All right, now, here is a polysaccharide. And would this be an amylose or an amylopectin, I wonder? Well, it looks to me like it's branched, right? They're not all just in a straight line. Amylopectin is what it is. And glycogen would be similar to this, all right? A branched chain polysaccharide. And every one of these little rings would be representing a unit of glucose. And you can throw more on what's here. I mean, you know, they had to stop when they filled up the screen. But anyway, there it is. All right. Now, carbohydrates. Hallmarks of carbohydrates. What are they? What are the elements in a carbohydrate? Carbon, hydrogen, and oxygen. And what else? What about hydrogen, oxygen? Somebody said it. 2-to-1 ratio. Right. So if it's that, it's carbohydrate. All right? Now, you thrown in other elements, well, it's not a carbohydrate. And if you don't have the 2-to-1 hydrogen-oxygen ratio, it's not a carbohydrate either. Lipids are going to be a good example of something that's not a carbohydrate. Lipids are what we commonly call fats. All right? Now, they are non-polar molecules. Now, if we go back to carbs a moment, carbohydrates have the ability to form hydrogen bonds. Lipids? No. Alright? Lipids are non-polar. So, what happens here? You put them in water, then go in solution. Right? If they're non-polar, what kind of interparticle forces are there between closely spaced adjacent molecules of the lipids? Dispersion forces, that's absolutely right. Alright. Now, common lipids that we're going to be concerned with, triglycerides, also known as neutral fats, phospholipids, and sterols. Alright, those are the biggies when it comes to lipids. So we have triglycerides, also known as neutral fats, we have phospholipids, and we have sterols. Now, triglycerides. Alright? The bulk of the fats, well, you know, when you're thinking about adipose tissue, this is the big thing, it's stored in it. What are they made of? They're made of glycerol, alright, which is an alcohol, and 3 fatty acids. Alright, that's what they're made of. Glycerol and 3 fatty acids. Now, what elements are we looking at here? Well, if we're looking at triglycerides, they're also going to be carbon, hydrogen, and oxygen. However, the hydrogens and oxygens are not in a 2-to-1 ratio. There's going to be a lot more hydrogens than there are oxygens, and it's not a 2-to-1 ratio by any stretch of the imagination. All right, so again, carbon, hydrogen, and oxygen, but not a 2-to-1 hydrogen-oxygen ratio. Okay? That's different. All right, now, here is kind of the basic part. But this is the glycerol part, which is the 3-carbon alcohol, and I would get concerned about that. And then stuck onto it are 3 fatty acids. Now remember, triglyceride, okay? Glycerol and 3 fatty acids. Now, what are fatty acids? Well, they are long-chain carboxylic acids. There's the prim and proper definition. Now, long-chain, what is the chain? It's carbon and hydrogen. So it will be a lot of carbons and hydrogens in a long chain. Chain of carbons, hydrogens around them. And out on the very end is this carboxyl group. Now, carboxyl, well, let's just a quick drawing here on the board. Alright, the carboxyl group looks like this. And you may think, oh, you know, unshared pairs of electrons. They probably can hydrogen bond. Well, yeah, they can. But if you stick a big carbon-hydrogen chain out here, which is extremely non-polar, these things are not really going to go in a solution. They're really insoluble. And, of course, if it's an acid, well, it should be able to donate a proton. That one might come off under certain circumstances, but since it's relatively insoluble, very few of them will. All right? So, they're going to be really long carbon chain molecules that are essentially non-polar and not soluble in water. All right, so when it comes to fatty acids, we have a couple of categories here. We can have what are called saturated fatty acids, simply meaning they have the maximum number of hydrogens. Put another way, there will be single bonds between all the carbons. Each carbon in the chain linked together just with single covalent bonds with the next one. All right? So if it's nothing but single covalent bonds between the carbons, it's going to have the maximum number of hydrogens. It's considered to be a saturated fatty acid. And saturated fatty acids, well, more on them in a bit. Unsaturated. Unsaturated simply means they have one double bond between two of the carbons. So somewhere in that chain, there are two carbons that have a double bond between them. All right, and when you have to do that, you have to take off a couple hydrogens to stick it in there, and so therefore they don't have the maximum number of hydrogens. Now, the thing about an unsaturated fatty acid, whenever you put the double bond in it, that chain, that linear carbon chain, bends a little bit. All right? And that's going to have some implications for physical states here in a bit. And then finally, we can have what are called polyunsaturated fatty acids. Well, those have at least two or more double bonds in the carbon chain. So in there's going to be several double bonds, and every time you put in a double bond, you got to take out a couple hydrogens so they don't have the maximum number. And again, every time you put in a double bond, it bends a little bit. Now, what's with this bending business? Well, if you start bending, you can't get the things as close together as you can if they're nice and linear, if it's just a saturated fatty acid. So now, if you're looking at a fat, a triglyceride, like lard, that is made up of primarily nothing but saturated fatty acids, what is the physical state at room temperature? It's a solid. Now, it's a nonpolar molecule. So what kind of interparticle forces are there between the adjacent molecules? Dispersion forces. And if it's solid, would they be strong or weak? They'd be fairly strong. All right, now, what if you have triglycerides that contain mostly unsaturated and polyunsaturated fatty acids with those bends and twists in the chain? You can't get them as close together, so those are probably going to be a liquid at room temperature, like an oil, all right? Say like canola oil, all right, which has a lot of polyunsaturated fatty acids in it. Why? Well, again, what are the interparticle forces between the molecules? Since it's nonpolar, they're dispersion forces, and if it's a liquid, strong or weak, they're weak. They're not as strong. All right, so there you go. If you start the bending and twisting that you get when you put in the double bonds, you can't get them as close together. So they're not going to form strong dispersion forces. So oils tend to have more of the unsaturated, polyunsaturated fatty acids in them. Solids tend to be mostly saturated fatty acids. All right? And there you go. All right, so as we've said, if you have only saturated fatty acids, They tend to be solids at room temperature. Why? They form very strong dispersion forces that hold them in fixed positions. If they have unsaturated or polyunsaturated fatty acids, they tend to be liquids at room temperature, what we commonly call oils. The dispersion forces are weaker. All right? And there you go. Here is an example of a saturated fatty acid. Now again, I'm not going to expect you to draw it out for me, but in any event, what have we got? Well, we've got this long chain of carbons and hydrogens. All right, let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think you'll probably find that stearic acid is what that's called. And as you might guess, beef fat or tallow, that's largely the fatty acid that's in it. So you have triglycerides there that would be made of 3 of these, and the molecule of glycerol bonded together. All right, and there you go. And so nice long linear chain. You know, you can easily pack triglycerides made up of this very close together, and at room temperature, it's going to be solid, and you probably know, like fat on a roast or a steak or whatever before you cook it is pretty solid. All right? Now, here, and this is mislabeled, 1, 2 double bonds. Now, every time you form that, remember, you got to take out a couple of hydrogens. But also, what happens when you put those double bonds in? The chain bends. Now, why is this not as labeled? That's not unsaturated, that's polyunsaturated, right? Why? It's got 2 double bonds. If it's unsaturated, what did we say that meant? Just 1 double bond. See? You have to watch. Sometimes books make mistakes. They did here. But in any event, there you go. Now, here we have a triglyceride. Now, 2 of these, this one and this one, here's the glycerol, there's the 2 fatty acids, those are saturated. Nothing but single bonds. Here is an unsaturated fatty acid, and there it is with that bending. Now this one, well, it's hard to say. Probably would be a solid at room temperature, but it'd probably have a really low melting point. Okay? Now, if it were made of 3 unsaturated fatty acids, it'd be a liquid at room temperature because those bends would keep the thing from getting very close together, keeping the molecules a little further apart. All right, triglycerides. What are they made of? If you broke them down, what would you get for your efforts? A glycerol and what? 3 fatty acids, all right? All right, and the fatty acids could be either saturated, unsaturated, or polyunsaturated. What's the difference between them? Saturated, no double bonds, they're all singles. Unsaturated, 1 double bond. Polyunsaturated, 2 double bonds. All right, what elements make up triglyceride? Carbon, hydrogen, and oxygen. And if we go back here, as you can well see, there's only 2 oxygens in this whole thing. So it's hardly a 2-to-1 ratio between hydrogen and oxygen, right? Even though it's carbon, hydrogen, and oxygen, it's not the 2-to-1 hydrogen-oxygen ratio, so you know it's not a carbohydrate. Okay? Alright, so now let's go on to the phospholipids. Now this just takes the triglyceride and kicks it up a notch. What are they? Well, first of all, they are a major component of cell membranes. So when we talk about cells and we talk about cell membranes, we're definitely going to see the phospholipids again. And so, what are they made of, and what is their claim to fame? Well, again, they have glycerol, all right, that 3-carbon alcohol. They have 2 fatty acids, only 2. The third fatty acid is replaced with something that you all know and love so well. A phosphate group, or phosphate ion, basically, is attached to the glycerol. Alright, so what have we got? We've got glycerol, we have two fatty acids, and we have a phosphate. Now, before we go any further, let's make a list of what elements are here. Alright, carbon, definitely, right? Because glycerol and fatty acids have lots of carbon. Hydrogen, again, glycerol and fatty acids have hydrogen. Oxygen, again, glycerol and fatty acids, a bit of oxygen, not much. But there's one thing that's unique here that we didn't find in a triglyceride. What would that element be? Phosphorus, exactly. Because what is the formula of the phosphate ion? PO4, right? Aha, phosphorus and oxygen. All right, there you go. So what elements are going to be in a phospholipid at a minimum, carbon, hydrogen, oxygen, phosphorus. Now, in addition, some phospholipids will also have a nitrogen, but just one. All right? Some will also add a nitrogen. So, it could be a phospholipid if it has carbon, hydrogen, oxygen, nitrogen, and phosphorus. All right? But only one nitrogen and only one phosphorus. All right? There you go. Now, that's pretty simple, isn't it? Heavens, yes. All right. Now, here is kind of a basic structure. There's the glycerol. There would be the two fatty acids. But where the third fatty acid was on a triglyceride, we now have a phosphate, and here we've thrown in an amino alcohol. There's the nitrogen. There you go. Now, here is another little tidbit about these. Here's another way to represent it. All right, we have this ball thing we're calling the head, and then we have these tails. Now, where are those coming from? Well, let's just go right back. The fatty acids, the two fatty acids, are the tails. And as we noted in that prior slide that we just looked at, the tails are nonpolar. Nonpolar. Well, anytime you string together a long hydrocarbon chain, you're dealing with something that's nonpolar. Now, the head is made up of this part, the phosphate, and if it's there, the amino alcohol, the one with the nitrogen in it. That is going to be polar. So, we call that the head. Alright, the head is polar, the tails are nonpolar. Alright? Now, some other terms we need to add to our lexicon. Alright, the head, because it is polar, is what we could call hydrophilic. Alright, let's just write that term up here. Come on. There we go. Alright. Now let's see. Alright. Alright, the head is polar, and it is hydrophilic. Alright, meaning it likes water. Why? Because it can hydrogen bond with water. Alright? So that end of a phospholipid molecule can hydrogen bond with water. It wants to associate with water. Now, the tail, which is made up of those two fatty acids, is very non-polar. Alright? And it doesn't like water, right? Because things that are non-polar don't mix with water. They can't form any kind of common interparticle force with it. They are hydrophilic. phobic. And, you know, if something has a phobia, well, it's something it's afraid of, right? It wants to get away from it. Right? You know, if some nasty snake comes slithering through the door, what would you all do? I figure most of you jump up on the desk and scream, right? I know I would. I can't stand it, I suppose. But anyway, there you go. Heads are hydrophilic, tails are hydrophobic. And that's going to be very important when we come to putting these things together to form membranes, as we'll see. Because the heads are going to be on the surface, where they can associate with water, and the tails are going to get buried down in the middle, because they don't like the water and they want to get away from it. But they like to associate with each other, because the tails can certainly form dispersion forces with each other. And there we go. All right, but more on that later. All right, we're just kind of setting the table today, so to speak. All right, so there we go. Phospholipids. Now here are a couple of phospholipids, and this is drawn in a model that is, if you will, made up of little balls to represent carbons, hydrogens, oxygens, nitrogens, and phosphorus. And so here we go with the glycerol part. There's the head. There are the tails. And you notice this one is an unsaturated fatty acid, so it's got that little bend in it, which of course determines how close you pack these things together. And this one is a polyunsaturated fatty acid. You get to look at that. Okay? So here again we have like the head up here, and then here are the tails. This is bipolar or hydrophilic, and this is hydrophobic. Okay? So there we go. Now, a sterol. This is a third class of lipid. And we all know and love this one. What are sterols? Well, they're wax-like structures. They're waxy. So it's solid at room temperature. It's kind of a waxy-like material. And it contains, at its heart, 4 fused carbon rings called a sterane skeleton. I'll show you a diagram of that here in a bit. Now these carbon rings, well, they're carbon and hydrogen. So I wonder, would they likely be polar or non-polar? Well, if it's carbon and hydrogen, what do you think it is? Non-polar, right. Okay, at its heart, it's definitely non-polar. All right, the most common example of a sterol for us, cholesterol. All right, that's the one that we make. That's the one that we make. Yeah, we get it in the diet, but we make the stuff too. And we need it, because here again, it's going to be very important in cell membranes along with phospholipids. So we're going to see that one again. So you can't get by without some cholesterol. Yeah, you can get too much, but you've got to have a good bit of it, really. There is the sterane skeleton. All right, it's these 4 fused rings, and in every one of these little spots, there's a carbon there, and there's at least a hydrogen associated with it. So this is just a condensed way to draw it out. You don't have to draw it out. But, but here again, you see it coming down the street as broad as life and twice as natural, you ought to recognize it's a sterane skeleton. And all the sterols are going to have this. Even plants make a sterol. They don't make cholesterol, but they make a sterol. All right? Here is cholesterol. Now this is all drawn out with all the carbons and all the hydrogens in its full glory. And there's just one little measly oxygen somewhere, which is escaping me off the end. Oh, it's right here. Now that little group right there is slightly polar, but all the rest of this is uniformly non-polar. So I wonder, if you stuck this stuff in a membrane, what end of the thing would be pointing up to hydrogen bond with water? that end right there. That's it. All the rest of it's buried down in the nonpolar part. All right? Well, more on that later. We're not going to worry about that today. But this is a very nonpolar molecule when you get down to it. And it is a solid at room temperature, so it obviously has rather strong interparticle forces between closely spaced adjacent cholesterol molecules. And what would those interparticle forces be, I wonder, if it's a nonpolar covalent molecule? Yes, dispersion forces. Right. Okay. See how that just keeps turning up again and again. All right, here's a little summary chart for lipids. All right, and you got this in your book, and you probably can't read this. It's too small. But anyway, triglycerides. What are they made of? A glycerol and what? 3 fatty acids. All right? Now, are they polar or non-polar? Non-polar. All right? They are non-polar. What elements are in a triglyceride? Carbon, hydrogen, and oxygen. Are the hydrogens and oxygens in a 2-to-1 ratio here? No, they are not. All right? Where do you find them? Well, this is the most common lipid in the body. This is what's largely stored in adipose tissue, which we'll chat about in the lab if we haven't already. Phospholipids. What makes them up? Glycerol. How many fatty acids? 2 fatty acids. What else you got to have? Phosphate. And you may also have an amino alcohol, which has a nitrogen. So what elements are in a phospholipid? Carbon, hydrogen, oxygen, phosphorus, maybe nitrogen. All right? How many nitrogens are there likely to be? 1 per molecule. How many phosphorus per molecule? 1. All right? Now, where do you find them? They're in membranes. Sterols. Where do you find them? Well, what are they made of? The 4 fused carbon rings, right? And cholesterol is the best known example for us. It is a very nonpolar substance. Elements, carbon, hydrogen, 1 oxygen. That's it. All right? Nothing else. And it is nonpolar. It's also going to be found in membranes. All right? Well, that's simple. All right, now, proteins. Well, proteins are really big macromolecular substances. High molecular weights. Huge molecules. What are they made of? They're made by stringing together in a chain amino acids. So proteins are made of amino acids. Now, an amino acid, obviously it can do a couple of things. If it's an acid, it's got to act as a proton donor. But it has 2 functional groups. They all have to have at least one of these. An amino group, NH2, which can actually act as a proton acceptor, and a carboxyl group, that's the COOH, that can act as a proton donor. Now, interesting is it not that an amino acid can act as a proton donor, which is an acid, but it can also act as a proton acceptor. And what was the substance that could do that? What was it called? A base. It has the properties of both an acid and a base. And there's a term for that, and that term is amphoteric. It's A-M-P-H-O-T-E-R-I-C. A-M-P-H-O-T-E-R-I-C. Amphoteric. Has the properties of both an acid and a base. And amino acids fit that mold. Another substance that does is water. You know, water can do both too. It can donate protons, it can accept them. Okay? It's also amphoteric. Here's the basic structure. Alright, there's the amino group on that end. There's the carboxyl group on that end. And then we've got this CH and the R up there. Well, the R could be anything. And in the simplest form, that's going to be another hydrogen. But it could even be a ring, a carbon ring, something like that. There are lots of other things that can go on there. There's at least one amino group, one carboxyl group on an amino acid. They all have that. Some of them actually have two amino groups. Some may have more than one carboxyl. Here is another one. This is what's called cysteine. You don't need to remember that. You know, here is what it's got. And you notice now what elements are we looking at here? Well, in every case, we just go back, we've got carbon, hydrogen, oxygen, nitrogen. All right? Every amino acid has to have those. Carbon, hydrogen, oxygen, nitrogen. Hydrogen and oxygen ratios are 2 to 1. No, it's not even close. And you can also have some other things thrown in. Now this one, the cysteine, oops, went the wrong way. All right, that one adds sulfur to the mix. There are a few others that may have a phosphorus. All right? So when it comes to amino acids, it's always carbon, hydrogen, oxygen, nitrogen. Sometimes you'll see a sulfur. Sometimes you may see a phosphorus. All right? But the hydrogens and oxygens, never 2 to 1. Never. Okay? Now, what can we do with those? Well, we can take those amino acids and we can string them together in a chain. And we can make what are called peptides. Now, what's a peptide? Well, a peptide results when you join at least 2 or more amino acids together, and by way of what's called a peptide bond. All right, now, here's another common theme. When you put together monosaccharides, what did you have to take out in order to do it? Water. When you put together amino acids to form a peptide, what are you going to take out? Water. So peptide bond formation is also a dehydration synthesis, because you're removing water every time you stick on another amino acid. Now, guess what you have to do if you want to break it apart? If you want to take a peptide and break it back into individual amino acids, what are you going to have to do with the water? Add it back, right? And what did we call that process of breaking something apart when you add water? Hydrolysis. That's right. You know, lysis means to break apart. The hydro bit, water. You add water back, you break it apart. There you go. That breaks the peptide bonds. Now, peptides are usually 50 amino acids or less. A chain of no more than 50 amino acids. Then we got a no man's land. And anything that's more than 50 but less than 100 is probably called a polypeptide. And then we get to proteins, and they're usually 100 amino acids at least or more, and it's usually going to be more, in a chain. You know, that's the only difference. So you start stringing amino acids together and you get a peptide. If you go, say, between 50 and 100, you got a polypeptide. And if you go 100 or more, well, you've got a protein. There's the difference, really. How many amino acids are in the chain? And we just start with that amino acid chain. And, of course, if you've only got a couple, well, you can call it a dipeptide. It's just 2 amino acids joined together by a peptide bond. If you throw on a third one, it's a tripeptide, and so on. I wouldn't get too concerned about all that, you know, because, no big deal. All right, here's a peptide bond. That's one amino acid residue, as we now call it. Here's the other. Here's the peptide bond in the middle. What do we have to take out in order to form it? Water. All right? No, I'm not going to expect you to draw it, so don't go into heart failure over that. Just know that it results from dehydration synthesis. When you put together the two amino acids, you're taking out a molecule of water. Now, proteins. Well, proteins have a hierarchy of structures. And we need to know what these mean. Hierarchy implies what? One level is built on the ones below it. Alright? So a higher level structure is built on the lower level structures that come before it. So let's start at the base, and that is the primary structure. Now what about that? Well, here's what it means. It refers to the number and sequence of amino acids. Number and sequence of amino acids. Now, for any peptide, polypeptide protein, it's going to have a set number of amino acids, and they're going to have to come in a specific order. There are 20 different amino acids. 20 different amino acids. So as you can see, you've got an almost limitless number of combinations you can come up with. Because the number varies considerably, as does the sequence of the amino acids. Alright? So that's the primary structure. The number and sequence of the amino acids. The specific number, the specific sequence. That's primary. Alright, so linear chain. Here it is. Now these little chiclet-like things would represent an amino acid residue. There's the peptide bonds between them. There it is. There's the primary structure. Alright, you've got a certain number of amino acids, and they're in a particular order in which they come. Now, the primary structure gives rise to what's called the secondary structure. Now, if you change the primary, that's going to change the secondary a bit. Alright? Secondary is, in other words, built on primary. So that sequence of amino acids has implications for how this turns out. Now there are two possibilities here. There will be areas of a peptide in which you get a zigzaggy kind of arrangement. That's called a beta pleated sheet. Excuse me. And thank you. And then there are others that tend to give you a kind of spiral, corkscrew, sort of spiral staircase arrangement. That's called an alpha helix. Now, what makes the difference? Well, it's the amino acids. If they're the small amino acids, those tend to favor the zigzaggy pleated sheet. If they're bigger amino acids, they tend to favor the spiral, the alpha helix. All right? So here again, it depends on the specific amino acids. Now what forms it? Something that will warm the cockles of your heart. Hydrogen bonds. But now this time, the hydrogen bonds are forming within that molecule because it's so big. It can start bending and folding on itself, and where the hydrogen bonds can form, well, that determines whether you get the pleated sheet or you get the helix. And, again, it depends on, well, what order are they in? Because the order they come in determines where those hydrogen bonds can form. Alright, there you go. And it's all built, as we said, on the primary structure. If you change the primary structure, you're going to change the secondary. Now, tertiary. Oh, yeah, here we go. Beta pleated sheet, spiral, alright, and again, as you can see, the red dots representing the hydrogen bonds. Where they can form really depends on the amino acid sequence. If you change that, they're going to form in different places. You're going to get a slightly different secondary structure. Now, the tertiary structure. This is the overall shape of a polypeptide or a small, simple protein. Alright? What happens here? Well, the alpha helix or the beta pleated sheet starts to fold. It bends and folds on itself into some three-dimensional shape. That shape might be like a sphere, like a ball. All right, what forms it and holds it? Well, once again, hydrogen bonds are responsible. And in order to get the hydrogen bonds in the right place, you've got to have a particular amino acid sequence. Now, what does that mean? Well, the shape is dependent on the secondary structure. And the secondary structure was dependent on what? The primary. So if you go back to the primary, and you alter the amino acid sequence, what have you done? You've changed the secondary structure, you've also changed the tertiary structure. Why do we worry about the shape? Because function is dependent on shape. If you change the shape of a protein, you alter its function. Now, that's a very important take-home message. Shape equals function. If you alter the shape, you alter the function. Now, here's an important term to add to your growing lexicon, and I think I even asked this on the test, as I recall, the term denaturation. What does it mean? Well, if you're talking about denaturing a protein, what are you doing? Changing its shape. That's all you're doing. That's all you're doing. Changing its shape. And if you change its shape, what happens to its function? It's changed and probably lost. Now let's take an example that I know you can relate to very nicely. Alright, crack open a raw hen's egg. What drops out on the dish or counter or wherever you break it? What do you see? The yolk, and it's surrounded by what? The white, the egg white. How would you describe the consistency of raw egg white? Sticky, slimy stuff, right? Kind of almost liquid-like. It's a solution. It's pretty viscous, right? Now, what happens if you had taken that egg and hard-boiled it? Now, crack it open. What do you see this time? A solid stuff. Gelatinous white solid, right? The egg white. What did you do when you heated the egg? You denatured the egg white. The egg white is a protein. Okay? It's an albumin. It's a protein. Little spheres. When you heated it, they unwound. All you did was change the shape. That's it. You didn't break it down. It still has the same primary and secondary structure, basically. You've disrupted the tertiary structure when you boil it. Now, what is the function of that egg white in the egg in the first place? What did Mother Nature have in mind for that? Well, it was to protect and nourish a developing chick embryo, right? You know, we just happen to take them and, you know, consume mass quantities, as the coneheads would have said. Well, they always called fried eggs fried animal embryos, remember? I'm old, so I remember the coneheads from Saturday Night Live, but anyway. What about that hard-boiled egg? Suppose you had just coddled it a bit, and it was a fertilized egg, and you flipped it back into some cackling old hen. Is she going to hatch a chick out of something like that? I don't think so. Why? You denatured it and it no longer is functional. That's it. That's all there is to it. And when you denature a protein, that's all you do is change the shape of the molecule. You don't break it down. You didn't hydrolyze it. All you did was alter the shape. But when you do that, what happens to the function? It's changed and probably lost. Alright? Now, kick it up another notch. So let's get to this. Here's the tertiary structure business. So there it is. Part of it's the zigzaggy part. Part of it is the helix, you know, and there it is. The way it bends and folds on itself, and there's the three-dimensional shape, which dictates its function. Now, some other proteins have got one more level. They all have primary, secondary, and tertiary, but some of them are made of more than one peptide or protein, and those are going to have something called quaternary structure. Now, again, it's shape. But it's the overall shape that results when you put together two or more polypeptides into a complex molecule. All right? Now, what's a good example of a protein with a quaternary structure? Well, you've all heard of hemoglobin, right? Where do you find hemoglobin? In your blood, right? In your red blood cells. That's there to bind and transport oxygen. Hemoglobin is made of 4 peptides, 4 polypeptides combined together. And you got to combine them together to have a particular overall shape if you want the stuff to function properly. Now there are some variant hemoglobins. And they don't work as well as hemoglobin A, which is the principal hemoglobin we've got in our red cells. All right? So, for example, there's one called hemoglobin S, and if you've got very much of that, you're going to have sickle cell trait or sickle cell anemia. And you don't transport oxygen as well with that one as you do with hemoglobin A. All right? So there we go. And the only difference is really one amino acid on a couple of those polypeptides. But anyhow, it's a complex protein. It has 4 polypeptides. They have to combine together in a particular shape in order for it to work properly. All right, that would have quaternary structure, and once again, shape equals function. All to the shape, all to the function. All right, and so here's kind of an example. There's one polypeptide, there's the other. You put them together in a particular way, and you've got a particular quaternary structure. And there it is. Now, as we said, all have primary, secondary, and tertiary. They only have quaternary if you're combining more than one polypeptide together, like in the case of hemoglobin, which has actually 4 polypeptides. All right, there we go. Now, nucleic acids. And we're not going to say a lot about these today. But nucleic acids make up the genetic information in a cell. And there are 2 principal kinds, and they are RNA and DNA. RNA stands for ribonucleic acid. DNA, deoxyribonucleic acid. Now, these are large molecules, especially DNA. Huge, huge molecule. All right? But, in any event, what are they made of? Well, the basic thing we're going to link together to form these will be nucleotides. All right? So remember now, amino acids were the building block for peptides and proteins, but when it comes to nucleic acids, the basic building blocks are nucleotides. What are they made of? Well, they have really 3 components, 3 parts. There's a sugar. All right? Now, the sugar is either ribose or deoxyribose. Remember those? How many carbons were in ribose and deoxyribose? 5. Therefore, they were known as pentases, right? Okay. Now, we have, so if it's RNA, it's going to have ribose. If it's DNA, it has deoxyribose. They have a phosphate. All right? What elements are in a phosphate? Phosphorus and oxygen, right? And then there's a purine or pyrimidine base. Now, let's just take a look at, there's ribose. I wouldn't worry about that. Deoxyribose. You notice there's no oxygen here. This comes up there, that's the name, deoxyribose. I wouldn't be concerned about that either. Here's the basic structure of a nucleotide. Sugar and phosphate, and then here's the base. They have a sugar-phosphate backbone, as it's called. Sugar-phosphate backbone, and then they have the base attached to it. And so we have a single strand, like most RNAs are. There's the sugar-phosphate backbone. There are the bases. All right? Here's a double-stranded arrangement. And what, I wonder, with the little dotted lines between the bases here in the middle indicate they're hydrogen bonds. So hydrogen bonds show up again here. All right? So if it's a double-stranded nucleic acid, it's going to have hydrogen bonds between the bases. All right, here are the bases. Now, there are purine and pyrimidine bases. Here are the purines. Adenine and guanine, I wouldn't worry about that for now. Thymine and cytosine, don't get in a heart failure over that. We're going to see that again. All right, the dots would represent hydrogen bonds between them, and they pair in a certain manner. What are the elements that you see in these pyrimidine purine bases? Well, carbon, which is understood. If it isn't there, it's carbon. Hydrogen, oxygen, and nitrogen. Right? Carbon, hydrogen, oxygen, nitrogen. So what other elements are you going to find in nucleic acid between carbon, hydrogen, oxygen, and nitrogen? Phosphorus, right? Phosphate, remember that? Okay. Yeah, because all the sugars they're carbon, hydrogen, and oxygen, right? Okay. All right, and we're about that. And then we got one more category, and that's an energy compound. Now, what about those? Energy compounds are there as a way of storing and releasing energy. They're substances or molecules that are in a cell, and their whole reason for being storing and releasing energy. How do they store it? Phosphate bonds. How do they release it? Break the phosphate bond. Simple enough, isn't it? Here is the preeminent energy compound that you're going to find in a cell. It's called adenosine triphosphate. Adenosine triphosphate. It is typically abbreviated ATP. All right? ATP, adenosine triphosphate. Now, if it's triphosphate, how many phosphorus atoms do you suppose are going to be in a molecule of ATP? 3. So if it's something that has only 3 phosphates, it's probably ATP, right? Isn't that simple? Yes. All right. Now, what other elements have we got? Carbon, hydrogen, oxygen, nitrogen, and there are 3 phosphorus. Now, that's all there is to it. All right. Not a terribly huge molecule at that. Here's an adenine, there's a ribose, and there are the 3 phosphates, and that's it. That's ATP. Now, what could be simpler than that? All right? Very simple. And here's just kind of a little summary chart for our organic compounds, our classes of organic compounds. Keep that in mind. And we have that practice sheet. In fact, there's 2 of them. And since I ain't have time to go over them today, I guess I'll have to put the answers on the web page, won't I? So, Wednesday then, we'll have a little test. As I said, I think I've got it right now. And I don't know, I'll change it and all. But anyway, it's easy. It's really actually easy practice sheets. But there are like about 40 multiple choice and 5 short answers, and you shouldn't have a bit of trouble with it at all. But anything we've seen or done is fair game, starting with lecture number 1. I wouldn't be surprised if you don't have, the definition of anatomy and physiology and homeostasis and some of that stuff to show up. All right? Well, actually, we're out of time, so we've suffered enough for today.